Okay, hello everyone. So today we're going to cover chapter 8, sections 1 through 3, which is all we're going to cover in chapter 8. So I'm just going to call this slideshow chapter 8. So chapter 8 is really about confidence intervals. That's what the title is. In the center of a confidence interval is something called a point estimate. That's the best one number estimate for the parameter that you can come up with. So first we're going to start by talking about the point estimates and then confidence intervals, and then we're going to talk about how big a sample size needs to be in order to get an estimation within a particular tolerance. And so that's the last thing we look at. Just some heads up. The idea here that we're going to be doing is we have a sample. So we have sample, and we want to estimate a population parameter. That's going to be our guiding question. How do we estimate a population parameter? So maybe we want the average weight, the average waiting time, of all calls to the IRS or to the Verizon customer service line. What's the average of all that? See, we don't know the population parameter. All we have is a sample. And so how can we be sure that our population parameter is within a particular interval? Okay, let's get started. A point estimate is a single statistic used to estimate a population parameter. So the parameters, and this estimation is very context dependent, or problem dependent. If you want to estimate the mean, then the best thing you can do is just take the mean of your sample. If you want to estimate a proportion, what percentage of the population is left-handed, female, anything like that, the best thing you can do for a point estimate is just use the sample proportion there. Okay, let's take an example. A Gallup poll was taken in which 1,487 adults were surveyed, and 43% of them said that they have a Facebook page. Based on that result, find the best point estimate of the proportion of all adults who have a Facebook page. And so we have a sample of 1,487, and the sample proportion was 43%. 43% of them said they had a Facebook page. Based on this result, find the best point estimate for the proportion of all people who have a Facebook page. So assuming that the Gallup poll was that Gallup was careful with its sample, and that they gave us a good representative sample, it is likely our best estimate, our best guess for the population proportion P is just going to be 0.43. That's the proportion, or 43%, exactly what we have there. All right. Okay, now let's talk about confidence intervals. So that was the point estimate. That's the best single thing we could do. single number we could produce. Confidence interval. This confidence intervals are always of the form the point estimate. In this case, it was p hat plus some error, and then p hat minus some error term. And that forms your confidence interval for proportion. Okay. A confidence interval, or interval estimate, is a range of values used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated CI. So we want to get to that true value. We're going to use a confidence interval to do that. Confidence level. Confidence level. The confidence level is the probability, so it's this probability, 1 minus alpha, such as 0.95 or 95%, that the confidence interval actually does contain the population parameter. Assuming that the estimation process, which in this case is just going to be sampling, is repeated a large number of times. So the confidence level, 95% confidence, says if I were to repeat my sampling and the way that I made my interval, then I would expect the true value to be contained 95% of the time. The confidence level is also called the degree of confidence or the confidence coefficient. Here's some common confidence levels. So relationship between confidence level and alpha. The following table shows the relationship between the confidence level and the corresponding value of alpha. The confidence level of 95% is the value used most often. Notice that corresponds with alpha equals 0.5, which is our usual definition, which comes from our usual definition of significance. Interpreting a confidence interval. Now we must be careful to interpret confidence intervals correctly. There is a correct interpretation and many different and creative incorrect interpretations and of the confidence interval. So for example, you have this confidence interval. Notice what goes in the middle, P, the population proportion. We are trying to estimate the population proportion here. So here's the correct response. We are 95% confident. Just go ahead and use that language. 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. That's a good way to say it. 95% confident, and leave it at that. There is, and then this one here tries to explain something, over-explain it, but in a way that just it isn't true. There is a 95% chance that the true value of P will fall between 0.405 and 0.455. That's not accurate. In order to determine the chance that that parameter P will fall in that interval, you need to do a very different sort of calculation than what we're doing. This is not actually what we are finding. 95% of sample populations will fall between that. See, that's not 95% of sample populations. What are they talking about? There's only one. Oh, sorry, sample proportions. 95% of sample proportions will fall between 0.405 and 0.455. That's not true either. That's not what we're finding. That's not what the theory suggests. We are talking about first of all, we're talking about the proportion, the population proportion falling into that interval, not the sample proportion. Okay. Process success rate. That is what we're talking about. The process of computing the confidence level. A confidence level of 95% tells us that the process we are using should, in the long run, result in confidence interval limits that contain the actual population proportion 95% of the time. So in this case, a sample was taken and a confidence level was produced 20 times. 5% is 1 in 20. Notice that one of those intervals does not actually contain the true population proportion. We don't know in general, we don't know what the true population proportion is. And so we don't know if we have one of these instances in which the true population proportion is not in our confidence interval. And that's why we can only say we're 95% confident that the true population proportion lies within that interval. Okay, now here's a tool that's very important in constructing a confidence interval. The critical value. A critical value is the number on the borderline separating the borderline separating well, let's see, what do we have here? Separating, well, we'll say z-scores. Z-scores that are significantly low or high from those that are not. And so the total blue area is alpha, and Z alpha is the particular z-score whose area to the right is alpha over 2. So that the total area on the sides is alpha. Example, finding a critical value. Find the critical value z of alpha over 2 corresponding to a 95% confidence level. Well, if it's a 95% confidence level, then alpha is going to equal 0.05. Because 1 minus alpha percent is the confidence level. I guess you would multiply that by 100. Okay. So that's alpha. So what I'm looking for now is z of 0.05 over 2. That is, I'm looking for the z value that has an area to the right of 0.25. Now, what I can do is I can look up on the table for something that has an area of 0.25. It will give me a negative number. I'll make that number positive, and that will be my z value. So let me go ahead and look at that table. Go to Canvas, Stats, go to my lookup table, negative values. I'm looking for 0.25. 0.025. I find it. Where do I find it? Oh, there it is. See right there? And it's at negative 1.96. So this thing here is negative 1.96. So that means that my z value, I make it positive, and because of symmetry, the positive is going to have the same amount of area to the right. So z of 0.025 equals 1.96. This from table. Here are the common critical values. 90% confidence interval when alpha equals 0.1 is 1.645. 5% is what we found, 1.96, and you can see 99%. All right, so we talked about the critical values. Now we're going to talk about the margin of error. When data from a simple random sample, that'll be an important thing to remember. We always want to have a simple random sample. That's necessary for this theory to work. When data from a simple random sample are used to estimate a population parameter, such as proportion or mean, the difference between the sample statistic and the population parameter is an error. Okay, so the difference between the statistic that we calculated and the proportion that we would like to know is an error. The maximum likely amount of that error is the margin of error. We denote that by E. There is a probability of 1 minus alpha, such as 0.95, that the difference between the statistic and parameter is E or less. That's what we're trying to achieve. This is pretty much a definition for E. Here are the margin of errors for the 3 situations that we will consider in this chapter. The first situation is that we're trying to estimate the population proportion, denoted by P. The margin of error is going to be the critical value, Z alpha over 2, where alpha corresponds to confidence level, and then multiply that by an approximation of a standard deviation, which we may, this may seem familiar to us. So the P is from data, and the P hat is from data, and the Q hat is also from data. Now, This bit right here is an approximation of a standard deviation. So something like sigma is approximately square root of p hat q hat over n. Now, it makes sense to multiply this by a critical value because remember, a critical value is something like data p minus p hat minus p over our standard deviation. Maybe I'll go like this. Mu p hat over the standard deviation. And so if I multiply by the standard deviation, this thing here is approximately p hat minus mu of p hat, which equals p hat minus p, because mu of p hat is going to be p. And so this error does in fact give us this difference. This critical value ensures that the difference is within alpha over 2. Yeah. At least within, with probability alpha over 1 minus alpha. Okay. Then there's the mean. The next situation is when we're trying to estimate the mean using, and we know the standard deviation. This is not a very common situation. We generally do not know the standard deviation. The confidence level here is going to be a z-score. This is normally distributed. It's going to be your z-score times, and then there it is, the standard deviation again. Remember that we are dealing with a sample mean, and the standard deviation of a sample mean is the standard deviation of the population, which is sigma, which in this case happens to be known, but we divide that by the square root of the sample size, which is n. Let's just start filling in that notation now. So p hat is the sample proportion. Q hat is 1 minus p hat. N is the sample size. It's all about this sample. Sigma is the population standard deviation. What else is there? Okay, nothing yet. Nothing more yet. The next situation is when you are trying to estimate an average, but you do not know the standard deviation. This is far more common. If that is the case, then your margin of error is going to be t sub alpha over 2, signifying that you will be using a t distribution, which we will talk about, times an approximation of the standard deviation, s, that is the sample standard deviation, divided by the square root of n, similar to what we had before, and we multiply that by this t critical value, this t-score. We will talk more about the t distribution in a moment. In order to look something up on a t table, you need the degrees of freedom, which is going to be 1 minus the sample size. These are how you find your margin of error, And the margin of error is used with the point estimate to construct your confidence interval. Let's see. Let's be a bit more specific here, and then we will take an example. So, looking just at the population proportion, that is this first row and the previous table. The sample is a simple so in order to use this theory, it needs to meet the requirements. The first requirement is that the sample is a simple random sample. The conditions for the binomial distribution are satisfied. This is also required. There is a fixed number of trials, and the trials are independent. There are 2 categories of outcomes, and the probabilities remain constant for each trial. You need to make sure that this condition is met or nearly enough. There are at least 5 successes and at least 5 failures. So when we're talking about successes and failures, remember, we're dealing with a population proportion. If in your sample you don't have at least 5 of the 5 of each value of each category, 2 categories, so you need at least 5 of each category. If one of your categories is more rare than that, then this estimate may not be accurate. Okay. However, if those requirements are met, then you can find a confidence interval that describes the probable location of your population parameter, of your population proportion. So this right here comes from your sample, and this right here is also constructed from your sample and a critical value, which depends on your confidence level. Remember that the margin of error is constructed like this. Your sample gives you, and critical value and confidence level gives you everything you need to know about that. These are sometimes denoted like this and like this. Oh, and round to 3 significant figures. Okay, here is an example. We noted that a Gallup poll, 1,487 adults, showed that 43% of the respondents have Facebook pages. The sample results are n equals 187 and p hat is 43. Find the margin of error that corresponds to the 95% confidence level. The margin of error is this: E equals z alpha over 2 square root p hat q hat over n. Let's start with z alpha. I need to find z of alpha over 2. Well, alpha equals 0.05. I know that because it's a 95% confidence interval. So now I need to find z of 0.05 over 2, which is z of 0.025. Recall, we already found this value. We found it by looking at the table where there was a area of 0.025 to the left. That's easy to look up on the table. It gave me a negative value, and I just made that positive because critical values are always positive. This thing turned out to be 1.996. That's the first part of my margin of error. So my margin of error is going to equal 1.96 times the square root of P, which is 0.43, times Q, which is 0.57. All I did was I just subtracted 1 P hat from 1 and got Q hat. And then I divide by 1487, like that. And if I do that, I'm much quicker at putting this in my calculator than I am using Excel. So I'm just going to do that. 1.96 times square root of 0.43 times 0.57 divided by 1487 equals 0.02516. I'll go ahead and go that far. Find the 95% confidence interval estimate of the proportion population P. For that, I need P hat. P hat is 43%, or 0.43. And so the confidence interval is going to be P hat minus E, P hat plus E, which is going to be 0.43 minus this, enter, 0.404, let's see now, 3 significant figures is what it said. So that'll be, so I better make this a 5. Okay, comma, now add 0.455, and that's it. And so that's my confidence level. Based on the results, can we safely conclude that fewer than 50% of adults have Facebook pages? The answer is yes. Yes. We are 95% confident that the true proportion of adults with a Facebook page is less than 0.455, because we think that P, the actual proportion, is in this interval. If it's in the interval, it'll be less than this value, which in turn is less than 0.5, 50%. So if our actual population proportion is in this confidence interval, it is definitely going to be less than 0.5. And that's what they're asking, fewer than. Basically what we have here. Here is one statement that summarizes the results. 43% of adults have Facebook pages. That percentage is based on a Gallup poll of 1,487 randomly selected adults in the United States. In theory, in 95% percent of such polls, the percentage should differ by no more than 2.5 percentage points in either direction from the percentage that would be found by interviewing all adults. So the percentage that would be found by interviewing all adults is nothing other than the population proportion. And so they're saying that it shouldn't differ by 0.25 percentage points. And you'll see that's what we have right here. This is, if we were to convert this to a percent, it would be 2.5 percentage points. Okay, when analyzing results from polls, consider the following. The sample should be a simple random sample and not not an inappropriate sample. The confidence level should be provided. So in a result, make sure to see that the confidence level is provided. Is it 99% confident, 95% confident? The sample size should also be provided. Except for relatively rare cases, the quality of the poll results depends on the sampling method and the size of the sample. But the size of the population is usually not a factor. So whether the population is really big or just sort of medium-sized, like in the thousands, it doesn't really change much. Okay, caution, never think that a poll results are unreliable if the sample size is a small percentage of the population size. The population size is usually not a factor in determining the reliability of a poll. If I have a confidence interval and I want to find the point estimate or the margin of error, I just use these formulas. I take the upper bit of the confidence interval, add it to the lower bit, divide by 2. That is to say, I average these, and that will give me my point estimate. If I want to find the margin of error, I take the difference between the upper interval and the lower interval, and I divide it in half, and that gives me my margin of error. Here's an example. Finding a sample proportion and margin of error. The article, High-Dose Nicotine Patch Therapy, includes this statement. Of the 71 subjects, 70% were abstinent from smoking at 8 weeks. And they say that's a 95% confidence interval, 58% to 81%. Use that statement to find the point estimate, P, and the margin of error. All right, well, P hat is going to be the average of the two intervals. So that's 0.85 plus 0.81 over 2. And that's going to equal 1.39 over 2. 1.39 over 2 is 0.695, about 69.5%. Now they want us to find the margin of error. The margin of error is the difference between these two endpoints divided by 2. And so the difference here is going to be 0.23. Divide that by 2, and we end up getting 0.695. 115. So this is 69.5% is the point estimate, and 11.5 percentage points is the margin of error. Now let's talk about determining sample size. Finding the sample size required to estimate a population proportion. The sample must be a simple random sample. Remember that. It's very important. A simple random sample of independent sample units. When estimate of of the proportion is known. So remember, if you don't know the sample size, if you're trying to find a sample size, you probably haven't conducted a sample yet. This is something you do before you conduct the sample, before you take the sample. And so it's not uncommon that this thing here, p hat, will not be known. However, if it is known, then this is what you want to do. Now notice that this is just solving this equation here for this is just solving this equation for n. There's nothing magical about that. When no estimate is known, then do this. As it turns out, this right here is a worst case scenario. It comes when p equals 1/2. That's when you don't know anything about the population. The best guess is just 1/2. If p hat is 1/2, q hat will also be 1/2. Multiply both of those together and you get 1/4, or 0.25. What percentage of adults make online purchases? When the Mario Triola, who wrote a book that I like, was conducting research for a chapter in his statistics book, he could find no information about the percentage of adults who make online purchases, yet that information is extremely important to online stores as well as brick-and-mortar stores. If the author, Mario Triola, were to conduct his own survey, how many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? Okay, no more than 3 percentage points. Assume that a recent poll showed that 80% of adults make online purchases. All right, so we want to determine the sample size. N equals z alpha over 2 squared times p hat q hat over square root of e. Now, 95% confidence interval gives us our alpha. Alpha equals 0.05 under the 95% confidence interval, or confidence level. The 3 percentage points, by no more than 3 percentage points, prescribes the margin of error. E is going to equal 0.03. All right. Now, p hat is also given to us in this form here. 80% make online purchases. So now we can construct our our estimate of the sample size. So when alpha is 0.05, z is 1.96. And so what I need to do is square that and multiply by 0.8 times, what's q? 0.2 over square root of 0.03. Let's see what that gives us on 1.69 squared times 0.16 is what that's going to be, divided by second square root 0.03. And we end, right. Right. And so if we do that, we end up getting something that to me seems rather low. I'm just going to double check on that. Oh, not square root of e squared. E squared. My apologies. E squared. Okay, so that would be 0.03 squared. Okay, very good. Over here, copy that. Delete. All right, 0.03 squared. Now enter. Okay, there we go. This thing equals 682.951. Now, of course, I'm going to need to round up. Always round up in this case. I'll write that. Round up. And so, if I do any fewer than 683, I may not get the margin of error that I desire. So I need at least this much. Now, assume that we have no prior information suggesting a possible value of the population parameter. So in that case, we have n equals 1.96 quantity squared times 0.25. Remember that formula. When I don't know the population, an estimate for the sample proportion, I use 2.25. Square that. Now, if I do that, then I end up with 1,670.11. And then I always round up. So this is 0.68. So I would need 1,680 people in order to have the desired confidence level of, in order to have the desired margin of error of 0.03. So I'll write that. To get margin of error of 0.03. Okay, now we're going to talk about the proportion, a confidence level, a confidence interval of a proportion of a population mean when sigma is not known. And as was mentioned, this is the more common. This is much more common than when sigma is known. Sample is a simple random sample. Then either or both of these conditions are true. The population is known to be normally distributed, or n is greater than 30. Remember, this is the central limit theorem taking effect here. If that's the case, then we can go ahead and do our confidence interval. It's going to be the sample mean minus the margin of error as a lower bound, and as an upper bound is the sample mean plus the margin of error. Round to 3 significant figures. Oh, well, actually, no. There is a rounding rule. Yes, here's the rounding rule. So that should be deleted right there. If you're using the original data and you have to find the statistics of X hat and S yourself, then round the confidence interval limits to one more decimal place than is used for the original data set. If you are given summary statistics, when using the summary statistics of N and X hat and S, round the confidence interval limits to the same number used for the sample mean. Okay, so recall that the formula for the margin of error is T alpha over 2 times S over square root N. That T is a t-score from a t-distribution. We will now talk about this t-distribution. Student t-distribution. If a population has a normal distribution, so it has to have a normal distribution, then the distribution of t of these statistics here, of these t-scores, is known as a student t-distribution for all samples of size n. A student t-distribution is commonly referred to as a t-distribution. So the t-distribution is the distribution for these standardized population means, sample means, standardized sample means. Okay. Key points about the student t-distribution, degrees of freedom. Finding a critical value, t alpha over 2, requires a value for the degrees of freedom, or df. Degrees of freedom is usually a little less than the number of samples that you have, because there's some sort of restriction on the collection. In this case, that restriction is not very much. The degrees of freedom is n minus 1. Okay. What does the student t-distribution look like? Well, it depends on the n. When n is 3, notice that the distribution, the student t-distribution, is lower in the middle than the normal distribution. It is more spread out. So for small n, anyway, I think I'll say that later. So for small n, the student t-distribution is more squat, lower in the middle and higher at the tails. It has heavier tails. It's more spread out. As n increases to infinity, the student t-distribution approaches the normal distribution. So here's some key points. The student t-distribution has the same general symmetric bell shape as the standard normal distribution, but has more variability with wider distributions. And that's exactly what we would expect with small samples, not a whole lot of reduction of variance from the from averaging. Okay. The student t distribution has a mean of t equals 0, just as the standard normal distribution has a mean of z equals 1. The standard deviation of the student t distribution varies like the sample size. But it is greater than 1, unlike the standard normal distribution, which has a standard deviation of 1. And this goes back to it being more spread out. The standard deviation of sample of student t is greater than 1. It's more spread out. As the sample size n gets larger and larger, the student t distribution gets closer and closer to the standard normal distribution, as I said. All right, let's take an example. Finding the critical value of the t alpha over 2. Okay, excellent question. Find the critical value of t alpha over 2 corresponding to the 95% confidence interval. So, again, we have alpha equals 0.05. And so I am looking for t of 0.05 over 2, or just t of 0.025. Now, in order to find this, I could do this a few ways, and I'll do both of these ways for you. I'm going to go to the table. Notice that the third tab on the table gives me a t distribution. Here's my columns. Now notice that because I get a different curve with each degree of freedom, this has been simplified. Okay, now the area in one tail, let me just go back to this thing here. So with the 95% confidence interval, alpha equals 0.5. And so what that means is you've got alpha over 2 on one side and alpha over 2 on the other. And the total area is 0.5. So let's go back to the table here. So the total, let's say, area in one tail, area in two tails, the total tail area. So that's this right here. That's the table I'm looking for. And now I need to find my degrees of freedom. N equals 15, so the degrees of freedom is going to be 14. So I'm going to line it up, and I'm right there, 2.145. That's my critical value. 2.145, and that was from table. If I want to do it in Excel, it's much easier. Let's see where's Excel? There it is. Let's open new. Okay. Equals t dot dist. That's good. T dot dist, see what it says? X. No, I don't want the X. I want to put in area and get out a z-score or a t-score. So I've got the wrong formula. So let me just delete all of this if Excel will let me without yelling at me too much. There we go. So I'm going to do equals t dot There's the inverse. Okay, now, probability. Now, as usual, it wants the probability to the left. So that is going to be 0.025. Degrees of freedom is going to be 14. Enter. And there's the negative 2.14. Let me just make sure I did the degrees of freedom right. Yeah, 15. So degrees of freedom is 15 minus 1, which is 14. So I go back and notice that it is very, very close. Now it gave me a negative number because I was going to because it gives me area to the left. But because it's symmetric, I just make it positive. So I get 2.1445, I think is what I got there. Oh, 79. Which rounds to 2.145, which is just what I got. So this one was from Excel. All right, there we go. So I typed in t.inv 0.025 14 and pressed enter and got out that. Okay, determining the sample size now. So finding the sample size required to estimate a population mean. The required sample size can be found by this right here. Let's see. Dealing with unknown sigma, finding sample size. So there's a few approaches you can do if you don't know what sigma is. And remember, you haven't taken a sample yet, so you don't really have the sample statistic. The range rule of thumb can be used to estimate the standard deviation as follows. Remember, the standard deviation is approximately the range divided by 4. So where the range is determined by the from this sample, where the range is determined from some sample data. You haven't sampled yet because you don't know how much, but perhaps there is some sample data available. Start the sample collection process without knowing sigma, and using the first several values, calculate the sample standard deviation S and use it in place of sigma. The estimated value of sigma can be improved as more samples of data are obtained, and the sample size can be redefined accordingly. Or you could estimate the value of sigma by using the result from some earlier study. Example 7, IQ scores of statistics students. Assuming that we want to estimate the mean IQ score for the population of statistics students, how many statistics students must be randomly selected for IQ tests if we want 95% confidence interval that the sample mean is within 3 IQ points of the population mean. So that'll be n equals z 0.05 over 2 times let's go back to our formula. Sigma times sigma over over E, all of that squared. All right, so that is going to be, I already know my critical value for the 95%, for the 95 confidence level. The 15 is known to be, the sigma is pretty well known to be 15 for IQ tests. And then I divide by 3 IQ points. So this is going, and I square all of that. And if I do, I get that thing. Now square it. 96.04. And so the answer then is going to be 97. All right, confidence interval estimate of mu with known standard deviation. So this one, if I go all the way back to my trusty table here, which I think I would like to bookmark. Here it is. Bookmark. If I go back to this table, let's see, how do I get rid of that? There we go. If I go back to this table, I see that with a known standard deviation, it is a normal distribution, and I just use z, sigma, and square root of n. All right, so let me go back. Let's see. We go. Here we go. Okay, use the 15 birth weights of girls given below, for which n equals 15 and x hat equals 30.9. Construct a 95% confidence interval estimate of the mean birth weight of all girls by assuming that sigma is known to be 29 Hg. Okay. So, okay, so what's it asking? It's asking for a confidence interval. In order to find the confidence interval, I need a point estimate, x hat, which is 30.9, and I need a margin of error, which is z alpha over 2 times sigma over square root n. So this is going to be 1.96, because I've got alpha equals 0.05, times the standard deviation, which is known to be 2.9, divided by square root of 15. So that's my margin of error, and I'll go ahead and compute that. 1.96 times 2.9 divided by the square root of 15. Enter. And so I get approximately 0.455 5. And so my confidence interval is going to be 30 30.9 minus 0.4555, 30.9 plus 0.455. That's my confidence interval. And it is the same thing as 30.9 minus 0.4555. And so that gives me 30.4. Yeah, that's good. Notice I'm using summary statistics, so I'll just round to the same decimal place. And then on the other hand, I get this thing. I get this thing here. Okay. Oops. And 31.4 also. And so that right there is my point estimate. I mean my confidence interval. 95% confidence there. Okay, choosing an appropriate distribution. If you're dealing with so if sigma is not known and the population is normally distributed, then use a student t. Or if it's not known and n is greater than 30, then you can use student t. If sigma is known and normally distributed, or sigma is known and n equals 30, then you use normal distribution. And remember, if it's the population proportion, then use normal distribution. Okay, very good. All right, the rest of the slides are all example slides. So if you don't need examples, you're welcome to stop watching. But if you are interested in examples, please continue watching. All right, touch therapy. When she was 9 years of age, Emily Rosa did a science fair experiment in which she tested professional touch therapists to see if they could sense her energy field. She flipped a coin to select either her right hand or her left hand. And then she asked the therapist to identify the selected hand by placing their hand just under Emily's without seeing it or without touching it. Among 280 trials, the touch therapists were correct 123 times. Given that Emily used a coin toss to select either her right hand or her left hand, what proportion of correct responses would be expected if the touch therapist made random guesses? Whoops, not 1/5, but 1/2. 1/2 would be expected. If they just made random guess, they ought to be right, at least as random as the coin was. They should be right half the time. Using Emily's sample results, what is the best point estimate of the therapist's success rate? Well, that would be 123 divided by 290, which equals 123 divided by 280. and that's about 0.439. Not very good. Using Emily's sample results, construct a 90% confidence interval estimate of the proportion of correct responses made by touch therapists. All right, it wants a confidence interval. In order to find a confidence interval, I need to find my point estimate, which is going to be p hat, the 0.439, and then I need to find my margin of error, which is going to equal, now this is a population proportion, so it's going to be normally distributed. So that's going to be z of alpha over 2 times p hat q hat over n. Okay, now in order to find my critical value, I am looking for 1%. So alpha is 0.01. So I want to find area. So 1% of the area needs to be outside of my critical numbers. So that means I'm going to look up in the table, or maybe I'll use Excel, the probability that I put into Excel is 0.005. That's half of the total area, which is alpha, because I want the area in the fringes needs to be that much. So why don't I just go to Excel, a new cell there, equals norm.inv tab, probability is 0.005, mean, the mean is 0, standard deviation is 1. Enter. Negative 2.575. So that is, so z alpha of 2 equals norm inv 0.005, comma 0, 1. And that equals negative 2.575. Negative 2. What was it again? 575. 576. And then, of course, I'm just going to make that positive because of symmetry, and I always want my critical number to be positive. And so I'm going to get 2.575 times the square root of p is 0.439, q hat is 1 minus 0.439, which is 0.561. Divide that by 280 Divide that by 280, and that's my margin of error. I'll go ahead and put that in. 2.576 times the square root of 0.439 times 0.561 divided by 280. And I end up getting 0.0764. 3 significant figures. So the confidence interval then is going to be 0.439 minus 0.0764 plus 0.439 plus 0.0764. And so the confidence interval is going to be 0.439 minus 0.0764. It's 0.363. And then on the other hand, it is plus 0.5154. And so that right there is my confidence interval. And so what that means is that I am 99% confident that the true proportion P is within these two numbers. Okay. 2 more examples. All right, speed dating. In a study of speed dating conducted at Columbia University, male students were asked to rate the attractiveness of their female dates, and the sample of the results is listed below. 1 is not attractive, 10 is extremely attractive. 9 used a 99% confidence interval. What do the results tell us about the mean attractiveness rating made by the population of all adult females? Okay, so this is a mean attractiveness. So this is a sample mean, x hat. It wants, the first thing it wants us to do is use a 99% confidence interval. What do the results tell us about the mean attractiveness? Okay, so we want to make a confidence interval here. So I need x hat, which is going to be the mean of this sample, which I'll go ahead and put into Excel, because I'm going to need a standard deviation as well, which I do not want to have to compute on my calculator. Okay, let's see what we've got here. There we go. Split it like that. All right, now I'm going to go ahead and type in these numbers. I'll just say this is example 10. And here's my data. I'll put my data down below. All right. 7, 8, 2, 10, 6, 6, 5, 7, 8, 8, 9, 5, 9. Let's see, how much is that? Is that, the sum is 12. What about the count? Count is, no, the sum is 84, the count is 12. Okay, grand. So, this is going to equal the mean, not geometric mean, average. Average, like that. Enter. So the average there is 7. Very interesting. And now for the standard deviation. Let me just go ahead and put that mean. Okay. Now for the standard deviation, that is going to equal stdev.s is a sample. Go like that. Enter. And there's my standard dev. Enter. All right, so I have that. So why don't I just go ahead and make my confidence interval right here. E equals, well, okay. Now I need my Z alpha, don't I? So that's going to be Z alpha over 2. And that is going to equal negative, because it's going to give me a negative, norm dot inv, probability is 0.005, mean it's always a standard deviation here when it comes to critical values. So enter. So there's my Z. Well, now where did that go? Okay. Well, negative norm inv 0.00501. Enter. All right, and so now I've got E is going to equal equals this thing times my standard deviation divided by, oh, wait a minute now. I need to do a t-distribution here. This is a t-distribution because I don't have a standard deviation. So I need to change that. Okay, let me just delete all of that and come over here. Change this to a t. T alpha over 2. Rather than norm inv, it's going to be t, okay, equals t dot inv all right, probability 0.005, 1% degrees of freedom is 11, because it's 12 minus 1, equals, there's that. I forgot to put minus in. I'll go ahead and put in the minus to make it positive. Enter. There's my t distribution, my t score, my critical value. This is going to equal that thing times S divided by square root of n, not square root of n minus 1, square root of n. But what is n? N is 12, so I'll just go ahead and put in 12. All right, so there's my margin of error. And so I've got a mean of 7. So Let me put in my upper and lower. So lower is going to equal 7 minus equals, don't put in 7, put in the mean, minus that, and then upper is going to equal 7, oops, plus E. And there's my confidence interval. So CI equals 5.01, that's 3 significant figures, 8.99. What do the results tell us about the mean attractiveness rating made by the population of adult females? Well, it's biased to say the least here, because surely we'd expect the mean. Well, I don't know, maybe. So we're saying that with 99% confidence, the actual mean attractiveness is somewhere in here, which means that on average, most people are more attractive than the middle 5. In fact, the average, the middle 5, middle of the road, is not even in this confidence interval. Okay. All right, what happened here? Did I just copy this for no good reason? All right, I think I did. Okay, anyway, let's go on. Mean grade point average, assuming that all grade point averages are to be standardized on a scale between 0 and 4. How many grade point averages must be obtained so that the sample mean is within 0.01 of the population mean? So these are grade point averages. So I'm going to use n equals let's go find the formula again. Here it is. So n equals z alpha over 2 times sigma over e, all of this squared. And so because it's a 95% confidence interval, I know my critical value is 1.96. My margin of error is 0.01. And now I need a standard deviation. How many grade point averages must be obtained so that the sample value the sample mean is within that much of the population mean? And so I need an estimate of sigma and so in order to get that, we need, so we'll have sigma to be 1, using the range rule of thumb here. And so we need to take that and square it. And so if we do that, we get 1.96 divided by 0.01, which equals that. And if I square that value, I get 38,416. 38,000. Does this sample size seem practical? Not practical. All right. So there you are. Okay, everybody. Good luck on your good luck on the quiz. Okay, now I